Dear students, in this video we are going to learn about the complex numbers. We will start by knowing what is meant by imaginary numbers first. Let's consider one situation. We know that a quadratic equation have two roots. Now consider an equation x square plus 4 is equal to 0. If we go on solving, we have x square is equal to minus 4. But there is no real solution to this particular equation, since square of any real number is greater than or equal to 0, that is positive. So here x must be equal to under root of minus 4, which is surely not a real number. These numbers are called imaginary numbers. Remember, any number which is of the form square root of negative real number is an imaginary number. Now, how can we write these numbers? Under root of minus 4, right? It can be written as under root of 4 into minus 1, which is equal to under root of 4 into under root of minus 1. We write under root of minus 1 is equal to I hereafter. So, this number under root of minus 4 could be written as under root of 4 into I, which is equal to plus minus twice I. Similarly, under root of minus 11 could be written as under root of 11 into under root of minus 1, which is under root of 11 into I. So if we carefully observe, all of these numbers could be written as a real number into I, So hence a number of the form ki, where k belongs to reals and I is equal to under root of minus 1 is imaginary number. Now let's move towards complex numbers. Now numbers of the form a plus bi, where a and b belongs to reals and I is equal to under root of minus 1 are called complex numbers. Generally, complex numbers are denoted by small letter z. Now here z is equal to a plus bi, then we say that the real part of z is equal to a and imaginary part of z is equal to b. Let's consider one example. Z is equal to minus 3 plus 8i. So here real part of z is equal to minus 3 and imaginary part of z is equal to 8. Note that every real number is a complex number. But in this particular complex number, imaginary part will be equal to 0. They are called purely real numbers. Example 4. That number 4 could be written as 4 plus 0i, and obviously it belongs to complex numbers because it is of the form a plus bi, where a and b are reals and I is equal to under root of minus 1. Similarly, every real number could be written in the same form, and hence every real number is complex numbers, and hence we can say that the set of reals is subset of set of complex numbers. Also, every imaginary number is a complex number with real part equal to 0. When real part is equal to 0, the complex number is called purely imaginary number. Example 7i, that is 0 plus 7i. Obviously, it is a complex numbers. Now, let's try to learn one more property, that is complex conjugate of a number. If we have z is equal to a plus ib, then a number a minus ib is called complex conjugate of z, and it is denoted by z bar. Now, we can see that z is complex conjugate of z bar and z bar is complex conjugate of z. They are complex conjugate of each other, right? So here, this you can remember, like complex conjugate of z is the original number z. Now, if z is equal to minus 3 plus 2i, then z bar will be equal to minus 3 minus 2i. Here you can observe that for taking the complex conjugate, the real part is to be kept same, and we have to change the sign of the imaginary part of the number. Similarly, consider another example. If z is equal to 7 plus root 3i, what will be the complex conjugate of this number? Obviously, z bar will be equal to 7 minus root 3i. Right? So, we have kept the real part as it is and changed the sign of the imaginary part. If z is equal to 2, then z bar will be equal to 2 because imaginary part is already 0. There will be no change if we change the sign of that 0 here. If z is equal to 8i, the purely imaginary number, then z bar will be equal to minus 8i. So this is about the complex conjugates. Now consider this property. If z is equal to z bar, then z is purely real. That is, imaginary part of z is equal to 0. How can we prove this? Like, if z is equal to z bar, then z is purely real. Let z is equal to a plus ib, so z bar will be equal to a minus ib. So z is equal to z bar is given, so a plus ib is equal to a minus ib. Hence, obviously twice ib is equal to 0, and it gives us b is equal to 0. That is, z is a purely real number. So, similarly, if z bar is equal to minus z, then z is purely imaginary. That is, real part of z is equal to 0. How? I think you can find yourself on the same lines as we have done for the earlier property. Now, how to represent a complex number graphically? There is the graphical representation of the complex numbers is done on the Argand plane. Argand plane is just like the Cartesian plane, but in this particular plane, the y-axis is particularly for the imaginary part of the number and the x-axis for the real part of the number. Let z is equal to 3 minus 2i, and we will try to plot this number on the Argand plane. Now this is the Argand plane. Here we have 1, 2, 3, minus 1, minus 2, minus 3 on the x-axis. This is for the real part. And on the y-axis, the numbers actually are I, 2i, 3i, minus I, minus 2i, minus 3. That is, 1 unit is for I. Right? And now we represent this number. Now this given number, 3 minus 2i, how can we locate this? Right? So, on real axis, it is 3. On the imaginary axis, it is minus 2, right? So, this is the number z. So, this is the number z we needed, and we have plotted this number on the Argand plane. Similarly, let's consider another example. Z1 is equal to 2 plus 2i. So, again, we can locate that 2 and 2i, right? So, this is this number. Okay, so this is Z1. Similarly, we can plot any number on the Argand plane. Now consider Z is equal to a plus ib, and we will plot this number on the Argand plane. So this is real part and imaginary part we have plotted, right? So this is the number, right? Z. This is real part. This is imaginary part B. By Pythagoras theorem, we know R is equal to under root of a square plus b square. But this R is nothing but the modulus of the complex number Z. It is denoted by this mod Z. And this mod z is equal to under root of a square plus b square. This is the property of any complex number. Modulus of a complex number is equal to square root of real part square plus imaginary part square. Right? So here R or mod z is the modulus. Similarly, we can observe that tan theta is equal to b upon a. Tan of this angle theta is equal to b upon a. So theta is equal to tan inverse of b upon a. This theta is called argument of the complex number. Now this argument, if we take the value between minus pi to pi, this will be called the principal argument of the given complex number. We can use the branch of 0 to 2 pi also if we want. But in this particular video, we are going to use the branch as minus pi to pi. You can use the 0 to 2 pi thing also. Let's take one example. Z is equal to minus 7 plus 11i. We want to find the modulus and the argument of the given number. Here, the real part is minus 7 the imaginary part is 11. So obviously mod z is equal to square root of real part square plus imaginary part square, and that is equal to obviously 49 plus 121, and that is equal to under root of 170. Now what about theta? So we know theta is equal to tan inverse of b upon a, which is equal to 11 upon minus 7 minus 11 by 7. So in this way we can find out the modulus and the argument for any given complex number. Let's consider one more example. If z is equal to 6 minus 2 root 3i, and we have to find the modulus and argument, we write this number as a plus ib. So here a is equal to 6 and b is equal to minus 2 root 3. Mod z by formula is under root of a square plus b square, that is equal to under root of 6 square plus minus 2 root 3 square, that is equal to 36 plus 12, that is equal to under root of 48, and that is equal to 4 root 3. So in this case the modulus is equal to 4 root 3. Now what about the argument? Theta is equal to tan inverse of b upon a, that is equal to tan inverse of minus 2 root 3 upon 6, that is tan inverse of minus 1 by root 3. Now for minus pi less than theta less than equal to pi, tan theta is equal to tan minus pi by 6 is equal to tan 5 pi by 6 is equal to minus 1 by root 3. Understand this, that there are many values for which the value of tan, there are many angles for which the value of tan of that angle will be equal to minus 1 by root 3, but these are the two values, minus pi by 6 and 5 pi by 6, which lies in the principal branch of minus pi to pi. Can we use both of these as answers? Then no, we cannot. Actually here a is positive and b is negative, right? A is positive and b is negative. So if a is positive and b is negative, so we are talking about a positive and b negative, that is the fourth quadrant, right? That means the angle must lie in the fourth quadrant, and here the angle in the fourth quadrant is minus pi by 6, and that's why the argument is equal to, principal argument is equal to minus pi by 6 for the given number. Now if we have this number z is equal to a plus ib, we can talk about the arguments for the purely real and purely imaginary numbers. For purely real z, theta is equal to 0 if a is positive. Example, let's say z is equal to root 2. Now this number z is equal to root 2 is at this point, root 2, right? Obviously we can see the angle for this number is equal to 0, right? Now the angle is, the principal argument is pi if a is negative. Consider another number which is equal to minus 3 z1 here. If we see this number, right, this complex number, the principal argument in this case is equal to pi. So any number which is a negative real number, right, for that the argument will be equal to pi, and for any positive real number the argument will be equal to 0. Similarly, for purely imaginary number, theta is equal to pi by 2 if b is positive. That is, for a number, let's say twice I. Let's consider this number twice I here. So this number is here, right? Obviously you can see the angle is equal to 90 degrees. That's argument is equal to pi by 2. The principal argument is pi by 2. If b is negative, then theta is equal to minus pi by 2. The principal argument minus pi by 2. Like, let's consider this example, minus 4i. The number is here, right? And the angle is minus pi by 2. Now consider one more example. Find modulus and argument of minus 4i. Again here z is equal to minus 4i. So a is equal to minus 4, b is equal to minus 4. Modulus is equal to mod z, that is equal to under root of a square plus b square, that is under root of minus 4 square plus minus 4 square. which will be equal to under root of 32, and the value is 4 root 2. Now argument, theta is equal to tan inverse of b upon a. If we put the values, it is tan inverse of minus 4 upon minus 4, that is equal to tan inverse of 1. Now we know that tan pi by 4 is equal to tan of minus 3 pi by 4 is equal to 1. We have two values of theta lying between minus pi to pi, right? Two values lying between minus pi to pi, which satisfy that tan theta is equal to 1. But here a is negative and b is negative, so obviously our angle lies in the third quadrant. So out of the two values, the value minus 3 pi by 4 lies in the third quadrant, and that's why the argument is equal to minus 3 pi by 4. Note that in many cases you will have to find out the angles corresponding to the given value of b upon a, and we can use the formulas like tan of minus theta is equal to minus tan theta, tan of pi minus theta is equal to minus tan theta, and tan of pi plus theta is equal to tan theta, to find out the various values of the arguments. So all the best with the examples. Thanks.